So so last time we discussed the we discussed stochastic gradient descent, right? So gradient descent is essentially trying to figure out which side is the slope going down at every point on the hill. Okay, and the hill essentially represents the height of the hill from the sea level represents the error in your model. Okay, so so as part of as part of the gradient descent, all we are trying to do is trying to find out the place where the error is minimum by by going down the hill in that direction where the slope is minimum, or you can say that mm, slope is downwards, highest downwards, and that's what we say slope is minimum. Had it been upwards, we would say that slope is positive and slope is maximum. Okay, so we are trying to figure out those directions on both sides, x-axis, y-axis, or if you have more parameter, then we are trying to locate the the dimension. If you have more features, then we will be moving in n dimension instead of only 2 dimension. That's gradient descent. Now, in gradient descent, we had talked about something called batch gradient descent, whereby we, at every point on the hill, so when we start at a random point, and at every point, what we do is we find the slope in every direction, meaning in every theta or in every coefficient, or you can say model parameters. So we try to find that and then take the next step, which is which is the which is the change in every direction. So let's say we want to move 1 foot leftward and 1 foot forward. So what we'll do is we will move to a position which is 1 foot left and 1 foot front in a single step. Okay, so that's what we do. And while doing so, we compute the slope with respect to all of the points at every point of time when we are saying that this is minimum slope. The way we do is we compute the slope in a direction using all of the data points. That's our batch gradient descent. Okay, so that's what we learned earlier, and we found that one of the okay, so one of the ideas was to find a good learning curve, because at what pace should we go down, or should we, in what ratio should we move faster than in what ratio should we take a step in relation to the slope, because the steeper is the slope, the faster we should be going, right? And that's our learning curve. So the learning curve is always a challenge to find. So we'll talk about more about learning curve as you go ahead. So we generally use grid search to find a good learning curve, and we always limit the iterations. And once we find a good learning curve, maybe then we can uh, once we find a good learning curve, then we'll be able to find a good we'll be able to find good model parameters that minimize the error. All right, now, okay, so the other thing that we talked about last time is if number of iterations are too low, then we may not reach we may not reach the bottom of the hill so quickly, or we may not reach the most optimum solution. We will stop before we reach there. If number of iterations are too high, then our time may be wasted and algorithm may never converge. Okay, so most of the iterations are consumed in the last part. Towards the end, more and more iterations are consumed because there the since the slope is not that steep, therefore moving in every direction is really slow because the learning rate, the overall step size is a multiplication of learning rate multiplied by slope. Therefore, therefore, when the towards the end, the number of iterations are a lot of number of iterations are wa- wasted towards in the last phase. So even though algorithm may not converge and a lot of time may be wasted just in moving backwards and forwards. So if basically the number of iterations have to be very uh, they don't have to be too high. They can be okay. So that again becomes your hyperparameter. All right. A quick thumb rule to finding good learning rate is initially set the large number of iterations and interrupt the algorithm when the gradient descent becomes very tiny. Okay, and when norm of the gradient vector becomes very tiny. Okay, so here what we're saying is the at every step, okay, at every step the change here, don't get confused with this x with our features. Okay, here x represents the gradient vectors. All right, so at the point where the slopes in every direction, the summation of all the slopes after squaring them and then taking a square root, if that slope, overall slope, becomes gradient factor is nothing but um, slope in every direction. At every point, any point of time, if that slope, the norm of that vector represented by represent norm of all of the gradient descent in every direction, if that slope, the overall slope, the goes down below certain tolerance, one must stop. Meaning, the surfaces become very horizontal. Okay, so a good way to find the good learning curve is you start with a large number of iterations and you interrupt when the gradient descent is tiny. Okay, you have kind of hit the flat surface and okay, so the other thing is how to choose tolerance. Tolerance could be a very, very small number, which is kind of your acceptable, uh, acceptable error. Or you can define when you look at the tolerance, if it is the it needs to be something that is acceptable with respect to our solution. So it will be very tiny. Okay. So it's something that you are okay in the error. So that will depend on project to project. And this you can take a good enough approximation. Now, the second thing we need to understand is with respect to the convergence rate. What is convergence rate? We are converging towards the smallest point, the minimum point, and the convergence rate is basically uh, convergence rate means how fast we are reaching to the lowest point. Okay, so so initially initially the when the initially the towards the beginning of your iterations, the convergence is higher, as in the rate at which we are moving, the rate at which we are pacing ahead is generally higher towards the beginning of the iterations. So you can say that the batch gradient descent with fixed learning rate has a convergence rate of the order of inverse of iterations, meaning in the initial phases, when the iterations are low, the convergence is higher, and the iterations keep on becoming bigger and bigger. The convergence becomes slower and slower because the slope has become kind of flat. And even if you had a good learning curve, then also, sorry, even if you have a good learning rate, even then the convergence is inversely proportional to the number of iterations. Okay, so as a quick test in the previous one, right, we were talking about the tolerance. Here, if you decrease the tolerance by 10 times, okay, the number of iterations will become 10 times. Meaning, if your tolerance goes down, that means you will need more number of iterations. Okay, and there is an inverse relationship of the tolerance with, relationship with the inverse relationship with the tolerance and the number of iterations. Okay, so basically the point here is that you start with a good number of iterations, and then you interrupt when the gradient descent becomes tiny. Okay, so that way you can always figure out a good learning rate. All right. A question from Bintao. Could you give us a few example samples about it? Sure, sure. Um, Let me just take a look at the notebooks if we have something there. All right. So right now we don't have one. No worries, no worries. Okay, so just make a note of here. All right. All right. Another question from Noor is how do we interrupt the algo? The way we interrupt the algo is basically we put a if condition there that if epsilon is less than this, break. Okay. Usual our for loop break. That's all. Okay. So let me just go up and show you. So here, for example, that we are computing gradients, right? So the way we discussed last time, so you could always compute gradients square and then sum them up and then put a condition here if norm of gradients. I'm just putting a hypothetical one. Okay, we can create a function and then break. Okay, so this is what we call interrupting the algorithm. Good, good question. All right. All right, so this is something that we discussed last time also. So we talked about there were so the challenges with batch gradient descent is that the it is uh, s- it is slow when the training set is large. Why? Why? Because the gradient in every theta or the slope in every direction gradient in every theta or slope in every direction it's basically it's basically computed as the mean of root square mean of all of the slopes as in we assume certain values of at every point of theta we put the value of that theta in all of the equations, okay, or in all of the data points, and then we find out the slope. So for every theta rate of the change of theta, we compute as the mean of all of the how should I say all of the data points. Okay, so basically it is extremely slow and because extremely slow as in if you have say m data points or m number of records in the training set it is going to find out the the slope using all of the m data points and then compute the average of that. Okay, compute the root mean square of that. Okay, so and that's one of the reasons why we call the batch gradient descent as to be slow. So the and this is where the stochastic gradient descent comes really of use. So it just picks a random instance in the training set at every step and computes the gradients based on only that single instance. Now, this makes algorithm faster as well as you can train huge training set. So our algorithm becomes independent of how big our training set is. So it becomes really quick to do the computation and hence we can use algorithms like stochastic gradient descent in the real production, okay, in the real-time environment where we need to do the training on the fly. Okay, so so for two reasons. One, it is really fast. Second, it doesn't load all of the data in the memory because it doesn't compute in all using all of the data points. So it just picks. The way it goes is that for every in every direction, or for every theta, it tries to compute the slope using one of the random points, and then moves ahead. Okay, that uh, and the course correction happens by other data points. So it might look a little bit zigzag if you plot the two thetas, theta 1 and theta 2. So so it might look like a bit of zigzag. So initially it checked here and then computed the rate and figured out that it has to move to this direction. Okay, but why? Because of the individual data points deviation from the main, it might go a little zigzag. Okay, so that's why. So it initially it thought that it's better to go in this direction based on some data point. Then it realized that it's better to decrease theta 1 and decrease theta 2 this side, and here then again it realized that it is better to increase theta 1 a bit and decrease theta 2 a bit, and so on. And sorry, increase theta 1 and decrease theta 2. Here then again realized that it's better to decrease theta 1 and decrease theta 2, and so on. So you see that it's a bit of zigzag. Why? Because of the because of just checking with single record, it kind of get deviated. It kind of does a little bit of mistake. But because every time it picks up a random record, the chances of it going back to chances of it converging is still there. Okay, had it picked, let's say, the same data point, what it picked here, it'll keep on going in the wrong direction. Okay, or it could basically move till here or come back. So the idea with stochastic gradient descent is that it may not converge so easily, but it is going to be really fast. Okay, so now the when the cost function is not having a kind of a convex shape, then SGD has a better chance. Okay, so if if we draw the cost with respect to some theta, and our graph looks like this, that there are two minimas, the one global and one local, and then there are plateaus at every point of time, which may be confused as the local minimas. Okay, so when the cost function is very irregular, then SGD has a better chance of finding the global minimum than batch gradient descent, right? For example, here, let's say if the algorithm we started from this point, so it will go slowly because the slope is low. Okay, and then at this point the algorithm might think that it has reached kind of minimum error situation and would settle down. Okay, or may stop, because the here as it is moving here, it'll figure out that there is the epsilon is changing very slowly, the slope has gone down, and so on, and that's why it might settle down somewhere here. Similarly, if it's starting from the left hand side, let's say initial point is left hand side, so it might converge really fast, but it would stop here, which is not a global minima. It's a local minima, because the global minimum is this one. Okay, so gradient descent sometimes may not find the best possible solution, and stochastic gradient may help in that. Okay, because let's say it was here, and then let's say we started here, and then for checking the next record, it might jump here, or it might jump here, and it might realize that Or let's say for checking the next step, instead of checking in here, it checks here, meaning some random record, and it finds that we are there is there is the slope needs to be really sharp, so it might take a bigger step and come here. Okay, or let's say it is here, or it is here, and then next record it checks is somewhere down here, and it might realize that it may have to shift. So basically the sole idea is that the in stochastic gradient descent, it is basically jumping b- between the data points in order to avoid these kind of situations. Okay, so so on one hand, SDD is takes it might take a longer time to converge, but it may not get stuck in the plateau, or it may not get stuck in the local minimum. Okay, so what is the solution? Quickly, between the two, we have on one hand we have stochastic, and other hand we have batch gradient descent. Both have their pluses and minuses. So what do you think is the solution we discussed last time? Yes. Ross, Pavan, Noor, Kamal, Viddao, Balaji, Abhinav. So what is the solution? If so, on one hand we have batch gradient descent, right? On other hand we have stochastic gradient descent. In batch, at every point of time we validate, we find out the slope using all of the data points, all of the training data. And stochastic, we just check with one record. Okay. Yes, that's right. So if we take a hybrid kind of approach, which is, in other words, we could say batched SGD, or you can say micro batch. All right. So this is where the batch will that's where we'll talk about mini batch. All right. And okay. So one of the solution in this case, okay. So one of the things is one of the enhancements is with respect to simulated annealing, in which we gradually reduce the learning curve. Okay, the the steps start out at large. This helps us make quick progress and escape local minima. Then steps get smaller and smaller. This helps the algorithm to settle down at the global minima. Okay, so this is called simulated annealing because it resembles the process of annealing in metallurgy, where the molten metal is slowly cooled down. Okay, so there are a few more terms that we need to understand. So one is that one of the solutions is that initially have a huge learning rate. Okay, remember when we have a huge learning rate, what happens? That this one jumps backward and forward, right? So, and then keep on decreasing the learning rate. And so as it keeps on going ahead, as it keeps on finding the minima, it keeps on settling down, the learning rate starts becoming smaller, and kind of settle down. That's called simulated annealing. This is a bit of enhancement to stochastic gradient descent. Okay, all right. So we instead of only simulated annealing, we could have we could keep on changing or decrease or increase the learning rate, and there could be many such strategies with respect to the learning rate. Okay, we could keep learning rate as fixed, we could increase learning rate, or we could decrease learning rate. This is basically a part of learning schedule. Okay, this is the function that determines the learning rate. At each iteration, at each iteration is called the learning rate. And so every time, at every point of time, we consult learning schedule that what should be the learning rate. And it, and learning schedule is basically a function that we could use in order to so in our algorithm here instead of like at this point, let me, yeah, so it was the same. All right, this is the example with, okay, so you're talking about different learning curves, as in the different curves with respect to different learning rates. And here wanted to show you. So there could be multiple strategies with respect to learning schedule, and right. So here you can see that this eta is being computed. Eta is fixed, and we are passing eta. So instead of passing eta, we could create a function called here like define learning schedule. All right, and at every point of time we could pass the values of x or xb or other parameters, whichever we want to pass. And this one should give us uh, some let's say zero point 0.5 or whatever. Let's say it's fixed for now, and we're passing the learning schedule here as the argument, and we're calling this learning schedule. Okay, we're calling this learning schedule every time. Okay, so the core idea is that instead of having in these algorithms, we could have the learning schedule as the argument, and learning schedule is a function that dictates how to vary our how to vary the learning rate. Okay, so again, if the learning rate is reduced too quickly, we may get stuck in the local minima. And if the learning rate is reduced too slowly, we may jump around the minima for a very long time. So okay, and end up with the suboptimal solution. So we can create something called learning schedule, and then make it further more flexible. All right. Now, okay. Yeah, at each iteration, we call this function. Okay, good question from Kamal. Can we set, the question is, can we set the Let me just go through if it's providing us with the learning schedule. So it has loss, penalty. Okay. Okay. So here, instead of it letting us provide a function, it lets us provide these predefined kind of learning rates. One is called optimal, okay, and other is called inverse scaling, okay, and so on. All right. So it doesn't let us specify the learning schedule, but it does let us specify the kind of learning rate we are going to use. Okay. Though it gives us ability to define the initial learning rate. Okay. If we don't, okay. And yes. All right. So SGD regressor doesn't provide us with the learning schedule, but we could implement our own. I don't think it allows you to do that. That's what I'm checking. So here it says that it's a string and it should be optional. Therefore, I doubt that we can pass the function to it. All right. Let me undo whatever I was doing. But I saved already. Okay, here we are defined. Okay. So whatever I was explaining earlier, we had already defined here as an example. All right. So here's an example of the stochastic gradient descent with the external learning schedule. Okay. The epoch. Okay. Let me just go again. So what we have here is we define number of epoch. Epoch is nothing but each iteration we are calling as epoch. And then we have these are the learning schedule hyperparameters. Okay. As you have seen in this also, this one. All right. So at every point of time, what we are doing is instead of taking eta as fixed, we are using this learning schedule. Okay, we are using this learning schedule function to compute eta. And what we pass to learning schedule is as an argument epoch, meaning number of iterations we have reached so far, multiplied by number of records plus the I. Okay, and what is I? The I is ith uh, ith record we are at. So what we do is here for every data point m. Okay, let me just walk you through. So you can see that m we have computed here. Okay. So theta path underscore, this will be used here later on. M is the number of records in the training set, and we are calling the random seed. Now here, so here what we're doing is we are calling the random function here to just generate the initial values of theta. Okay, initial theta as in from where does our gradient descent start? That's the initial value we have chosen. And then we are saying go for these many iterations, go through every record, and if epoch is equals to 0 or and I is less than 20, then what we are doing is we are predicting y. Okay, and then all right, this is just for plotting. This is just for plotting. Okay. All right. So now next we are doing is generating our random integer. And then what we are doing is we are okay. So here we are generating a random data point from where we are picking the x and y, you see. So randomly we are picking a data point, and then what we're doing is we are computing the gradients. Okay, we are computing the gradients. All right, this is I think clear. So 2 by 2 into xi dot t and so on, and then we are computing eta using the learning schedule, and afterwards we are computing the theta as initial theta minus learning rate multiplied by gradients. Okay, so this is slope, this is learning rate, and this is going to be new theta. This was old value of theta, and then we are appending this new theta. Okay, and this we are doing for all of the value, total number of m times. Okay, so basically here total number of iterations are epoch multiplied by total number of records, and just that our learning schedule now is a function of two things: epoch and the total number of data points. Okay, and so the total number of data points. So yeah, you can see that it is inversely, the learning schedule is inversely proportional to the iteration we are at. Okay, so as the number of iteration keeps on growing, the learning rate keeps on reducing so that it does not jump off. Okay, learning rate keeps on reducing as the t is growing, so learning schedule will give us a learning rate which is really small, and hence it won't jump away. Okay, all right. I'm just wondering that why couldn't we why couldn't we just say things like this? Okay, and remove it from here. Okay, so the I is essentially we are using this kind of a formula. Okay, so So what we let's just, because I is only used probably here, nowhere else, right? And therefore, okay. So the learning schedule here says that we are passing total number of epochs, okay, ith epoch, okay, plus ith epoch multiplied by total number of m, okay, plus I, okay, okay. That also kind of, I see, I see. We are basically using this iteration in order to plot it properly. Otherwise, we could have actually said a number of iterations like this, okay? And or let me just say, are we using epoch elsewhere? Yeah, we don't need this. So we could have just said things like this. If you are not plotting it every point, we could have just said this, okay, and maybe like this, total number of iterations, whatever it is, and we could just pass that, okay? You could just pass ITR, all right? Let me explain again. So, okay. So this is the enhanced SGD algorithm, and this is something already being done by scikit-learn. So since we want to take a look at the algorithm itself, that's why we wanted to walk you through. Okay, so what does epoch mean here? Could we you have me simple? So epoch means number of iterations. Example of epoch could be, say you want to try it for 2000 times or 100 times. If you increase epochs, the overall time is going to be higher. Okay, so that's epoch. And now, since there is a fear in case of SGD that even when we are about to converge, it might jump away, right? In case of SGD, it might just jump away to another point. Therefore, it's important to keep on decreasing the learning rate so that when it's converging, the learning rate is also reducing. Okay, so on every iteration, what we are doing is we are decreasing the learning rate. And what we do here is we add this with some amount so that it doesn't divide by zero. Okay, it doesn't divide by zero. That's why we add this with T1. T1 is fixed value. We've just put some number. And we are dividing, say, T naught, which is 5. 5 divided by the current iteration. Okay, so we are saying that our learning rate will reduce with number of iterations. And how are we counting iterations? What are iterations? One is the, let me just undo this part as well. Okay, so here at any point of time in the loop, okay, if we have to keep on increasing count, okay, or we could actually do this kind of thing as well. Count equals 0, and here we could say instead of this we could say count. Okay, this is equal to, this is equal to count. Okay, we could also say things like count and count plus equals 1. Okay, so basically if you take a look at this, it's essentially the ith iteration from the above loop, because for each of the previous loops, it has gone by m times. Therefore, m multiplied by that, m multiplied by the, uh, okay, so m multiplied by epoch, let's say it's in epoch is 3, so this must have gone by 3 times, plus I means the current iteration. Okay, so that's what is. If you do not want to use this, you can actually create your own counter and use that in the function. Okay, all we are saying is we are computing learning rate using this learning schedule, and which is giving us the learning rate as inverse of the number of iterations. Okay, is it clear why we're doing that? So that's all we're doing, and we could actually do it in the for one loop, but we wanted to plot here. We wanted to plot at every point of time the values of m. Okay, that's fine. Yeah, I think that's what we're doing. So for I in the m, what we are doing is, okay, for the initial values of I, what for initial values of I, and if epoch is 0, okay, epoch would be 0 only in the first iteration, right? And okay, okay, so that's what we're trying to figure out. So basically we are trying to plot the initial values, and that's all. Okay, so I hope I was able to explain. Question from Noor is that where are we using nu theta? I hope that got answered, because at every point of time, this is the theta that we are, the whole objective of this function, this whole for loop, the objective is to find that theta. So every time we are reducing the theta. Okay, and basically here we are just plotting it, nothing else. All right, I'm just trying to see if this is being used anywhere. Yeah, you can at the end of it, you can check the value of theta, and you will know that it's close to our input. Okay, a question from Vinta. What does it mean by epoch? Could you have a sample? I hope that got answered. Question from Noor. For multiple features, same loop will run for n features. Okay, good, good. So it has multiple features. So when we are, most of this computation with respect to all other records happen here. Okay, so xi would have multiple features, right? And we are um, basically converting that into a vertical vector by transposing, and then doing the dot product with this, correct? With this, okay? So when we do that, for all of the features, this would happen. If xi has 50 features, then that would be multiplied in every iteration. Okay. All right. This is exactly the reason why we use linear algebra, because linear algebra or these dot products and things like that, they make our life really easy. Otherwise, you could imagine there could have been a couple of more loops here for every feature in the xi, and it could have been more complex. All right. A question from Abinta is, what is random int? Here it's generating us one of the I, as in from between 0 to m minus 1, it's giving us a number. Okay, let me just show you. It is generating a random integer for us. Okay, so we could say, so every time we do that, we might get a different one, correct? So it's generating something between 0 to 10. If we had only 2, it would give 1, it would also give 0, and so on. Okay, so it'll generate something between 0 and 1. Okay, this is like coin toss, 0 and 1. All right, great. I hope this was clear to you. A question from Noor, please clarify x underscore new b. Okay, so what we are doing here is we are computing the y predicted value. Okay, how do we compute y predicted value? Whatever is our x values, whatever is our x, the we compute calculated x new b. Where did we calculate this? Okay, just give me a second. Okay, so what we had done was we had added one. This is okay. And let's make a prediction using this. Okay, so x new b was with ones. Okay, we had added one there, and that was our x new b. All right, so what we are trying to do is for the x which is having 1 as well, we are multiplying thetas, which is we are computing the y predict. Okay, okay. No, I'm just wondering why it isn't x new b and x underscore b. I see. Okay, so here we have just picked up some two data points. Two data points. X new b is nothing but just two data points, and we are multiplying that with theta. Okay, and computing the y's predicted value. Okay, and okay, if I is greater than 0, then we make it blue. Otherwise, we make it red. Okay. All right. All right. So yeah. So what we are doing here is for every value of x. So we have at every point of time, what we are doing is okay at every m at for all the records, what we are doing is we are just a second. Theta should be 2, right? Yeah. Okay. All right. Let me just explain the plot. So here what we are trying to do is we are trying to plot x new, which is x new, which is the 0 and 2, okay, with y's predicted value, and this. Okay, so this is what we are trying to do. Just a second, why is this? All right, so this is what we are trying to do every time. Okay, so here what we're doing is for 0 and 2, we are computing the values of y and drawing the line. Okay, that's what we are trying to do. Okay, all right. So this section of this is basically for drawing these horizontal line, while this portion is drawing plotting all the plots. So on every iteration in M, what we are doing is for every mth iteration, what we are doing is we are uh, we are drawing this line. We are computing at x0 and x2, and then drawing this line, which is showing everything in between. For the current computed thetas, we are basically computing at this point, and trying. Okay, I think we got it. That's basically for drawing the learning rate kind of. Okay, so earlier the predicted value was going here and then here and so on. Okay, so instead of plotting the line for every each of these points, what we're doing is we are taking two extremes and drawing the line there. That is kind of showing us as a good how should I say, it's because everything is going to be in between these two data points and so on. Oh, all right. All right. Should I explain again? Do you want to understand what is xi and yi? Okay. Xi is the whole vector. Okay. This is xi. Xi is basically at that random point. At that random point, whatever we had selected. Okay. Every time it chooses some xi and yi and uses that for computing the thetas. All right. Okay, so let me repeat what I was saying. So we start with some we go over the whole iteration. This is nothing but an iteration variable, and then here we have just put one more loop so that our line becomes a straight, and as in the line we are able to draw it clearly. So, and here we are saying that we predict some value of y for our sample records 0 and 2, and then plot that. Okay, so at every ith iteration, we are going through this block of code. Okay, if epoch is 0, meaning the iteration we are at epoch iteration 0, then uh, then this would happen, as well as the I is below 20, then it will happen. Okay, Otherwise, afterwards, since the lines will become too dense, there is no point of plotting these lines. Okay. So it's just only in the beginning of the iteration that we are trying to do this. Okay. All right. So here we are saying that if I is greater than 0, then plot this. Otherwise, plot with red. That's this. And when will I be less equal to? Okay. So at zeroth point in the beginning, this is the situation. So initially the error is positive, and then it starts decreasing. So initially it's drawing as red because I is equal to 0 in initial. That's all. So it the initial line it draws is red, and rest of it in the blue. That's what it is. Was I able to explain the algorithm to you, the SGD in general? Okay, it's basically this part of the algorithm. Okay, so this is the one which we are using. Instead of saying alpha here, we are just putting the t2 in the numerator. That's all. Okay, so this is called optimal. Any questions at this? Yeah, go ahead, please. A question from Noor. One more question. If any feature does not have correlation, still it is used in computation. Um, until we are doubly sure that it doesn't have a correlation, still we should, as in, if it's not, maybe it has a correlation by the way of any other parameter. So we do use that as when doing the regression. So we still use that in computation. Let the algorithm decide by the end of it which ones are not of use, which ones are of use. Good, good. Is this algorithm clear, or Ross, Pavan, Noor, Kamal, Bintao, and Balaji? All right. Actually, the only cause of confusion here was that why we have this one more loop. Okay. So it's very clear that this loop is only required for for the plotting of the graph, as in we want to do things like this, that the ith, when we are starting the iteration, we would at, for every epoch where I is 0, then we would like to use this. Okay, all right. Okay, so these are the first 10 steps in SGD. So in our case, we have done how many steps? We have done first 20 steps. Okay, so in the diagram, we have plotted first 10 steps or 20 steps, you can say, and notice how irregular the steps are. Okay, so initially it starts like here, these are moving fast, and after a while it kind of settles down. Okay, so a question from Vinta is why we are saying this. Basically, here what we want to do is, in case I is 0, okay, in case I is 0, use red, otherwise use blue. Okay, let me see if I could write the same thing. Okay, let me just make it something of this sort. This will be okay, right? Correct? I think this is far more simplified for you. Okay. All right. So, all right, I just made it simple. I've just made it a single loop, so it looks okay to me. Just that. All right. All right. Let me just do again this portion, as in the random seed. You see that? Yeah. This is the one I've just generated. A question is, what is this portion? So we are saying that on the when the iteration has just started, so it's equivalent of saying if epoch equals 0, okay, style is r dash dash, else dash dash. Okay, let me just choose the same random seed so that the initial line is visible. Yeah, here. So this is the same thing. So we are saying that if here. Okay, so we are saying that if epoch is 0, then use red line, otherwise use blue line. Okay, Binta. Basically, we just want to plot this as red. And double dash means we want to draw it as dashes, not the strong line. That's all. Okay, I hope that this one is clear to you. So we are just going over the iterations and doing that. That's right. That's right, Noor. Okay, so all we are doing is at every step, we are calling the learning schedule, and then using the learning schedule, we are computing eta. And to learning schedule, we are passing the iteration, the ith iteration. And what it is giving us back is the learning rate, which is inversely proportional to the ith iteration. Okay, so yes, great. So to perform linear regression using scikit-learn, use SGD regressor class. SGD regressor class by default optimizes the squared error cost function, and this is how we use it. Okay, so SGD regressor does a very good job, and by default it uses some kind of learning rate, some kind of learning schedule, which makes sure that it converges. It should not jump around. Okay, and so what we're doing is, even if it's jumping around, we are ensuring the learning rate is low. So it's going to go slow as number of iterations pass. A question from Binta is, what's the difference between scikit-learn and sklearn? Sklearn is same as scikit-learn. The one that you see in the top, this is scikit-learn only. Okay, great. All right. A question from Noor is, can you explain penalty? So let me just see. I think we covered penalty, right? All right. Let me just walk you through the actual algorithm. Okay. So basically the L1 or L2, whether we want to do it absolute or we want to do the squared, that is the one. L1 means so penalty is that function that we use to compute the error. Okay. That's the function. Okay. So if we pass L1, all right, let's just take a look at what did we do? Yeah. So here, basically, when we are computing the gradients, this is the formula that will change. This is the formula that will change if we use L1 as penalty. This is the penalty for square one. Okay. This is that when we are using L1. Okay. This is for L2 when we're using, remember how we computed gradients? We differentiated the main equation. It became 2 by m, right? It was square, and then 2 came here, and we did that. And then what we did was we used this formula. So this formula will change in case of the L1. Okay. So yes, good question. Good question. All right. So our understanding is right. Okay. So yes, internally there would be a if condition, or maybe there is a function that's being called here at this point. All right. A question from Binta. What's the difference between array and random n or random int? Random n gives us n number of records, while random int gives us a single value. Okay. Good question. All right. So this is what we did. And all right, I'm just wondering why we said none. The penalty, okay, sorry. So there is something called, hey, so sorry, uh, Noor, for my earlier answer. So penalty is with respect to regularization, defaults to L1, L2. Okay, all right. I think we will discuss regularization soon in details, and I think that then it'll become clear to you. Okay, I'll also take a look at this. Loss function is something that I actually explained to you. Okay, so we have been using squared loss. So this is with respect to the loss function. This is the loss function part. Okay, the penalty is with respect to the regularization. I'll talk about regularization very soon. In our case, it is none. All right. So penalty is what we're going to discuss very soon. Loss is something that we've used. All right. So we use the squared loss, and yeah, sorry for the confusion. Good. So what we've learned so far is we have kind of used stochastic gradient, and we have made it more instead of running crazily, we basically optimized it by controlling the learning path, learning rate. Okay. All right. So let me just see what is variable. So what is y? Y are the all the these, and then what is y dot table? Y dot table is okay. So it has converted y from columns to the rows, right? If you see this 6.33 and 9.4, okay, all it has done is it has done the okay, okay. It has what it has done it has extracted all the values from there and converted into this. Okay, okay. So this is equal to all right. So y level is equal to this y transpose and getting the zeroth value. Okay, let's just see y dot table. So you can see that. Yeah. All right. So y level is equal to transpose of y and then converting that into a single dimension one. Okay. So y level converts a 2D array, which is vertical column, into a horizontal array. A question from Kamal: is there an easy way to confirm both are same? I think they should be. They should be. Can we just say y level equals y dot t and the g? You can see that all of it is true. Wonderful, wonderful set of questions. Okay, good. Let's move ahead. A quick way to see all of them are true. And can I do a reduce here? Question to me is, can I do? Yeah, I think this is right. Some should be good enough because there are, I think, 100 records. and the answer is 100. So yeah. Okay, so it took one as true, and that's how it did the sum. Or maybe you could do there was a function to do the frequency analysis, right? Count values or something, and you could use that. Okay, so now moving ahead, so we were able to successfully okay, so it gives some kind of warning, we can ignore that, and here we are saying, so from sklearn.linear model, we are importing SGD regressor, and then we are instantiating SGD regressor, passing the number of iterations. We are saying that there is none penalty, we are not regularizing it, and then we are saying eta as dot one, and then we are passing the random state. Okay, and then we are, whatever y we had, we are passing that as a normal vector. Okay, instead of column one, because it's going to internally do that translation. Okay, and then we are fitting it. Once we are done, then we are saying SGD dot intercepts and coefficients. Okay. A question from Mintao, how to decide how many columns will be converted into all of the columns. Okay, so I think Noor's answer is a very good one in that. Mm, the here basically whatever we have here, there is one column, and it essentially what it does is it converts it into a single dimension array. It is just opposite of the there was a function to convert array into columns, right? Instead of that, it basically does the opposite. Okay, so whatever number of columns you have, they all will get merged and continued into a single array. It's equivalent of saying serialize. Okay, all right, do a bit of tweaking around so you'll get the idea. Yeah, shape method was also there, correct. All right, so that was our stochastic gradient descent. So all we need to remember is that we can import SGD regressor from the sklearn linear model and then instantiate the algorithm, meaning create an object of the algorithm by passing the number of iterations, penalty, eta, and then we just need to fit this. Okay, fit it with the x and y. Okay, once it's done, we can take a look at the intercept and the coefficients. Great. All right. So I think this piece of code you must try typing by yourself, because it would help you remember this, because when you are doing computation, you would at least want to remember this piece of code, because rest of it you can always look up quickly. All right, thank you, Noor. Thank you for that input on NumPy. Wonderful, wonderful. All right, so we had batch gradient descent and we had the stochastic gradient descent. Now let's talk about something in between called mini batch gradient descent. The last gradient descent algorithm will, this is the last one, last variation of gradient descent. It's quite easy to understand if we both know the batch and stochastic. We already have guessed it, right? So instead of computing the gradients based on the full training set, as in case of batch gradient descent, or based on just one instance. Here, if you look at the record, here we just computing it on xi and yi, and xi and yi are based on not here. We are computing based on xi and xi and yi are based on a random integer. So we are just picking one record called xi and yi. Based on that, we were computing a single. We were computing the gradient descent based on the single record, single instance. So instead of computing the gradients based on the full training set, we use, or only one instance, we use mini batches. Okay, we use mini batches. All right, so it is basically slight improvement over stochastic, in which we pick up small batches, and using that we do our prediction. So mini batch, the main advantage of mini batch over stochastic is that we can get the performance boost from hardware optimization of matrix operations, especially when using GPUs. Okay, so okay, so mini batch is essentially okay, so we can parallelize the computation with respect to every record in the mini batch using the GPU, and that's how we are able to achieve the mini batches. Okay, the problem with the batch gradient descent was there were just too many calculations and it took a long time, while in case of stochastic we had to keep on uh, stochastic, it was jumping around a lot, so it wasn't converging so quickly. In case of mini batch, since we have to only compute the only do the calculation with respect to few records, therefore the we can easily get that computation done. In case the computation is over thousands of features or a complex one, then what we can do is we can use the GPU. What is GPU? GPUs are graphical processing unit. Earlier we used GPU for playing games and doing other graphical computation, and we realized that the idea of regression is very similar, includes the similar kind of computation, because it also has a matrix multiplication and everything. And those things are really well done using GPUs as well, because that one has been fine-tuned for graphical processing. As we had earlier discussed that the graphic, the way we were talking about, the way we talking about the NumPy and linear algebra, we realized that both of them representing the linear, the vectors and the matrices in the form of graphics was very much possible, and the so the computation with respect to the graphics are very similar to the computation with respect to machine learning. Okay, so we use in case of computational heavy environment, we use GPUs for the uh, heavy weightlifting. All right, but that will be required only in case there are too many features, and the computation then the computation will become really heavy. All right, so so all right, so that's one thing. So mini batch is, of course, as you have already predicted, it's less erratic than SGD. Okay, so especially with fairly large mini batches, as a result, it goes more closer to minimum than SGD. Okay, all right. So let's take a break for 15 minutes. All right. So should we start? Hi everyone, I'm back. So should we start? Are you able to hear me? Hi Ross, Pavan, Noor, Kamal, Balaji, and Abhinav, Pintav. Great, great to have all of you back in the session. Is everybody back? Wonderful, wonderful to have all of you back. So we're talking about the mini batch gradient descent algorithms progress. It is less erratic as compared to the stochastic. It's specifically if you have a fairly large mini batches, as a result, it goes more closer to the minimum than SGD. Okay, it's harder for mini batch to escape from local minima. Okay, as compared to a stochastic gradient, the mini batch, the chances of mini batch getting stuck with local minima is higher than the stochastic gradient. Now, let's take a quick look at in the notebook. All right, so here what we have is we are going in the same way. So we're going over the iterations, total number of iterations. And here we have just picked up some shuffled indices. And out of those shuffled indices, we basically uh, shuffled our data here again. And then what we did was in the range of mini batch, we are iterating, or we are doing an iteration here at this point, and we are picking up the some of the records here. Okay, all right, and that's it. At this point, we're computing gradients and computing eta using the learning rate, and that's all. Okay, so what we see here is this is the overall agenda, as in we are computing the theta as a result of it. So we are iterating over these number of iterations, then we are shuffling it, okay, shuffling the indices, and then um, here in basically we are creating the mini batches out of it and then iterating over that. All right, iterating over that, and that's it. Okay, so we are computing gradient descent using this, and yeah. So on every iteration, what we do is we break down the data set into the mini batches, and for each of the mini batch, we compute the gradients. That's what we're doing here. All right. So you can see that it has we just needed like 50 iterations and our results were there. Okay. So all right. So from the training set, we are just creating mini batches and we are computing thetas over it. So let's now just compare the paths taken by the three algorithms. One is batch, stochastic, and mini batch. This would give you a of clear picture of the two, clear picture of the three. Right. If you want to take a look at how do the how does the path look like? These we had already created, the theta path SGD, theta path MGD, and theta path batch gradient descent. So these three variables we had already created. Like here we were appending these thetas, right? So we had kept that the, both the value of theta 1 and theta 2, or theta 0 and theta 1, and then we have plotted all the three graphs. Okay, so what you see is the batch one is very consistent, right? So initially we start with some assumption of theta naught and theta 1, then it starts increasing both theta 1 and theta naught and keeps on going consistently, and then uh, after a point of time it decreases it increases theta naught while decreasing theta 1. So this is the optimum point for the batch gradient descent. So it's very consistent and slow as it goes beyond. Here, it's very slow because you can see the dots are consecutive. And here it looks like a straight line. It is further slow. Now, the mini batch one, this is the mini batch one, whereby the behavior is less okay, we'll talk about that one later. Let's take a look at the stochastic starts somewhere here and then just keeps on jumping back and forth, keeps on jumping back and forth, and reaches afterwards it reaches somewhere here, somewhere keeps on going around here. Okay, this is what it happens here. And in the end it keeps on roaming around here in case of stochastic. Now in case of mini batch, what happens is it's far more consistent than the batch one, sorry, than the stochastic one, while it is less consistent than the batch one, right? So it starts here, goes up, comes down a bit, then goes up, then and so on. So it keeps on going here and ends up here. So basically, the the min, the mini batch is far less erratic than the stochastic. Can see that? Mini batch is far less erratic than the stochastic. Okay. Okay. Question from Kamal. Why did batch not go directly towards minima? Why it went up and came down? Okay. So initially it realized that basically here also there would be at this point where how should I say? So basically it's iterating over values of theta 0 and theta 1, and you're thinking that why didn't it go from here to here, right? So it's basically that's the trick about it. So if internally if you see the because the relationship with the output may not be like this, right? May not be linear, because the error is kind of a square, is kind of in the square. Therefore initially it when it is increasing both of them, it's kind of getting rewarded, and that's why. Okay, so I think this would be more visually clear if we take a look at the error three-dimensional graph. Okay, then you will get an idea why it kept on increasing theta 1 first and then brought it down later. Okay. Okay, so because at a lower value of theta naught, but higher value of um, higher value of theta 1, but lower value of theta 0, this value and this value could be similar. Okay, this value and this value could be similar. If you think of the output as theta naught plus theta 1, right? So this value, how much is this? 3.7 plus 3.2, correct? Which is equal to close to 3 plus 3 is 6 and 7. This is 7, right? So here also it's 7. And if you think about this, which is how much? 4.2, and this is 2.8, correct? So that's also 7. So both the points look very similar to in the output. That's fine. Did I make sense to you? A question from Noor: is there a method to calculate the particular algorithm efficiency? Okay. And yeah, bigger question is, what do we mean by efficiency? Okay, while mini batch is very efficient, very as in very how should I say? It gives you correct results, but it is really really slow. Okay, sorry, while the batch one is really slow, but gives us the correct results. But mini batch is not that slow. It's a little faster, but it is more erratic. Then it requires again more number of iterations. Then we have a stochastic one. Stochastic is further more erratic, and therefore we need more number of iteration there. So there is no one way to judge the efficiency. Okay, question from that's why we use grid search mostly for these. A question from Kamal, but if we had a lower learning rate, then would it be straighter? Mm, maybe, but I'm not sure. I'm not sure. You'll have to plot it and then you'll get an idea. If we had a lower learning rate, will it be straighter? It could be straighter. It could be straighter. Hmm. It'll take a, yes, that point of time, it could take more time. Okay. Okay. So batch or mini batch, both are require a lot of computations. Therefore, important thing to realize is that we need to utilize. Okay. I'll go back here. All right. So what you see here is, let me go back here. All right. Yeah. So what we have here is that for every batch, in case of stochastic gradient descent with batch, as in mini batch one, mini batch gradient descent, what we have is that we are splitting it into mini batch, and then we are computing this. Okay. In order to make it a little faster, what we could do is we could do this computation probably parallel using the GPUs. GPUs have many processors, and GPUs provide a lot of computing power if you are able to parallelize. Okay, so probably this portion we could parallelize, as in done for each of the batches, let it be done parallelly. Okay, and that could be one of the reasons why would we want to use GPU in case of mini batches. All right, so probably we could compute the theta using multiple batches, And or here, if we could distribute this part onto multiple cores of GPU, then that could also be really fast. Okay. A question from Noor is, how do we use it? So we'll come back to the GPU part again. We'll talk in detail about how to set it up, how to use it, and so on. Okay, wonderful. Great. And now, so what we see is that we can clearly see the difference between the three algorithms. And so other than my observation, do you have any observation with respect to this? Any observations from your side? Okay. Stochastic is full khichdi as in, and the corresponding term would be spaghetti. Okay. It looks like a Brownian motion. Okay. A question from Bindao is that how to choose the value of mini batch size. Again, it's a hyperparameter, just like other parameters. And what we do is we start with small and do a kind of grid search that gives us a fair amount of idea about the mini batch size. All right. Great. So the first observation we had was all the three algorithms end up near the minimum. Okay, there's no doubt about it. The second observation is batch gradient descent path actually stops at the minimum. Okay, so batch one actually stops at the minimum. Both stochastic and mini batch continue to walk around. The batch gradient descent takes a lot of time to take each step. Okay, so you can see that just to take one step here, you can see there are so many iterations it goes through. So it takes a lot of time to take each step. Okay. And overall, while batch gradient descent takes a lot of time, both stochastic and mini batch can reach the minimum provided good learning schedule. So the point here is that stochastic and mini batch are also able to reach minimum, but in less number of steps, and therefore they can work well if we provide good learning schedule. Okay, so there is almost no difference after training. All these algorithms end up with similar models and make predictions in exactly same way. Okay, though there is a difference in the way all three algorithms work, but once we get the model, once we get the result, then there is no difference between the three algorithms. Okay, Because once you get the result, you don't really need to worry about which algorithm did we use. Okay, so the conclusion is that stochastic and mini batch are also equally good. Okay, are also equally good. There could be very minor differences in the output, the precision or the quality. Okay. A question from Kamal. What is the magnitude of increased time when we use stochastic versus batch? More importantly, since stochastic is less CPU intensive, is there any use case of not using stochastic? Okay, very good point. So mostly we end up using either stochastic or using the mini batch. Okay, but for most of the practical cases, we actually use stochastic because it is less CPU intensive and faster. And eventually, and most likely, it does settle down if we provide a proper learning rate. Okay, so um, in most of the cases, we do use this stochastic, and the only cases probably we might be using mini batch, as in the usual one, the the batch gradient descent. We might be using batch gradient descent for maybe improved precision. Okay, for those kind of reasons, we might be using this. All right. Okay, so here are the clear comparison of the four algorithm. Normal equation, that is something which we used earlier, the first one that we started. Okay, mini batch code is here. You can see the mini batch. Very good point, Kamal. Could we use the stochastic and reach to some precision and then improve it further by using batch gradient? Yes, that's also one of the strategy people do use. Okay. Now here a question from Noor is that what I understand is here we are calculating multiple local minima. Is that right? So let me just here we're not computing multiple local minima. We're basically doing the same thing. What we're doing is we are taking the subpart of X. Instead of taking one record, we are taking the mini batch. Remember, instead of saying I plus one, we are saying mini batch. Okay. And then the gradients computation we are doing using these. In case of batch, we were using the whole of the input data. XB shuffled and Y shuffled is what we used here, correct? All right. So instead of taking one record, we are taking the full of it. Okay. A question from Binta. Are there mathematical expressions to all these four algorithms? So mathematical expressions is only for normal equations, while for batch, stochastic, and mini, all three are represented as algorithms. Okay, all three are represented as algorithms, and all three use this kind of a formula everywhere. Okay, so this is something that you can keep in mind. 2 into x into xt dot x dot theta minus y. Okay, so this was our end result. All right. So in all these three, batch, stochastic, and mini batch, this formula was used. Okay. While in case of normal equation, we used a separate formula. Correct. We used this was totally based on the mathematical expression. So let's just compare these four algorithms. Remember normal equation? Normal equation did not depend on number of training, how big is your training set. This equation did not depend on that because we did not iterate over record. Instead we differentiated and equated it to 0, and then using the equation solving ways, we solved the equations. Okay, that's what we did. So no matter how many records there in the input, it was able to do it really fast. So for large M, only the normal equation was slow, while stochastic, sorry, can you hear me now? Okay. So here what we have is, okay, let me repeat again. All right, so we are comparing the four records. Let me, actually there is, the button on my headphone got pressed automatically and it turned off. Okay, so we talked about four methods of four algorithms to compute the regression, as in compute the uh, com do the model predictions using in the regression. So we had normal, batch, stochastic, and mini batch. In case of mini batch, stochastic, and normal, the number of records in the input data set did not matter much. Okay, did not matter much. But in case of batch, we had to go over every record. Therefore, the batch was slower with respect to M, number of records, number of training records, than out of core. Out of core as in using the memory. So in case of normal equation and batch, both had to use the memory, while stochastic and mini batch did not have to use the memory. Okay, so here, if there are number of records are too high, does these two did not have to load that data into the memory, while these two had to load that into the memory. Okay, so basically, if the data is huge, the input data is huge, then these two will perform well, while these two will not perform well. Okay, so okay, out of core means out of core memory. All right. Now, what happens in case of large M? Meaning number of features are large. If you have too many features, normal equation will be slow, while batch, stochastic, and mini batch would be fast. Okay. So only in case of normal equation, the Number of features mattered. Okay, number of features mattered. Now, now there was no hyperparameter involved in normal equation, while in case of batch, remember which were the hyperparameters? Hyperparameters were learning rate and initial data point, correct? Learning rate and initial data point. In case of stochastic gradient descent, there were learning rate, initial data point, and then we had the learning schedule, right? And there were few more parameters with respect to learning schedule. Similarly, in case of mini batch, there was one more hyperparameter that how big should be our mini batch. So number of hyperparameters in case of stochastic and mini batch are more than two, while in case of normal equation there is no hyperparameter, and in case of batch there was learning curve and initial data points. Those were the hyperparameters. Okay. A question from Kamal. Why the choice of word out of code? Does it mean it will run out of memory in a single core computer? That's right. Okay. Now, do we need to do feature scaling or feature standardization? In in case of normal equation, no, but rest of them, it will be useful to have feature scaling. Okay. Remember our graph where we did not have feature scaling, so it looked the graph in which we plotted the concentric circles, right? So the if we don't have scaling, we won't be able to reach the optimum point quickly. Okay. Therefore, in case of gradient descent, all three, the scaling is required. Question from Kamal: is it possible to use multiple CPU for normal equation? Mm, I'm not sure because that the normal equation is about finding the inverse. Not in the normal equation, the biggest part that is time consuming is finding the inverse of a matrix. And computation of inverse of the matrix is, I'm not sure if it has been parallelized or not. If it is parallel, then the normal equation can be parallelized. So that's the main ingredients there. Okay. A question from Mintao. Can you show how to scale here? So scale is, remember that standard scalar, it's pretty straightforward. In the pipeline, we could just put scalar and we could scale. Okay. It will come back after a while. After three, four discussion point, the scaling would be there. So remember we created a pipeline, put the standard scalar and so on, right? In those cases, we would be using the scaling in that way. The third part is which of these are available out of the box in scikit-learn. Out of these, normal equation stochastic gradient descent is available out of the box in scikit-learn, while batch and mini batch is not available out of the box. All right. Does it make sense to you? All right. Now, so far, what we did was we did a linear regression, right? In case of linear regression, we assumed that our output is linearly dependent on input variables, meaning our y was linearly dependent of x, okay? Meaning there was no square or cube or multiplication. But in case of polynomial regression, in case our data is complex and our model is not fitting it, then we might have to take a look at polynomial regression. Okay. A question from Kamal. I think we can use the thumb rule if the number of features are few, use normal equation, otherwise we use stochastic. Okay, that's right. And the other thing is that normal equation could be used only if it's a linear regression. Okay, while gradient descent and others could be used in others as well. Okay, all right, great, great. Let's move ahead and let's talk about polynomial regression. Okay, so far we have looked at the data having a linear relationship or straight line. What if we have to fit non-linear data like quadratic equation? Okay, let's take a look. Okay, let's take a look. If our graph was like this, so you can see that if our graph is y is on y-axis and x is on x-axis. So it is y equals x squared minus x minus 2. So if x is 0, then the overall value is minus 2, correct? And if x is 2, then it is, this is 4, 4 minus 4 is 0, correct? And if x is minus 1, then again it is, this one is minus 1, so it becomes 1 plus 1, which is 2 minus 2, that is 0. Okay, so you can see that y would increase if the magnitude of x increases. Okay, if the magnitude of x increases, y would increase. All right, so this is a quadratic equation. Now if we make if we try to fit, let's say there are data points here, data points instead of the line, and we try to fit a straight line, it would never fit. It would never fit unless we are only looking at, say, smaller data. Let's say we are looking at only this part of the data, and then we are trying to fit a linear line. Then we would be happily fitting the line, and but after a point of time, we'll realize that we are overfitting our model, right? If we have a straight line and we have the actual data was of a quadratic equation, then and we are only looking at a smaller set of data and we are trying to fit it, then for that subset of data, it would look that our model is working perfectly. And but for rest of it, it might not look like that. Okay. So how do we handle this kind of nonlinear data? We can use a linear model to fit nonlinear data, okay, or add powers to each feature as new feature and train a linear model on extended set of features. This is called polynomial regression. Okay, this is called polynomial regression. Okay, let's first generate some nonlinear data. Instead of just keeping this equation, we're just adding some kind of noise. This noise is nothing but some random number so that this equation doesn't look like exact value. Okay, so when we generate that, this is the kind of data we get. So what we are doing is there are 100 records, m is 100. We are saying x equals 6 into random number, as in 100 rows and one column, and we multiply each of them by 6 and subtract by 3. Okay, so and then what we do is, okay, so we are basically generating the values of x between -3 to 3. Okay, that's what we are doing. We are generating value of x between -3 and 3. Okay, now the y, when we put x into this equation, y will look like this. Okay, we are again adding some kind of a noise here. Okay, for each of the y's, we are also adding some kind of a noise. All right. So we can use a polynomial features class to transform the training data and add squares of each features in the training set. Okay. So what it would do is basically the polynomial regression internally, what it does is we whatever features it has already in the training set, it basically adds square of each feature plus more combinations. Okay, so this is how it would look. So let's go back to the notebook and try running it. All right. So this is the data that we have generated: import numpy, import random number, then specifying a seed, generating x, generating y. If you want to take a look at how does the x look like, so you can see that x looks like this. So x's value is somewhere between minus 3 to 3. Okay, this is x, and there will be y similarly. And what we're doing is we're plotting this in blue with dots. Okay, with dots. What happens when I put dash here? I see. Oh, double dot is not there. Okay. And what about plus? Plus is there? I see. Cool. So this is how it looks like. This is the graph that we talked about. So what is our actual equation? Our actual equation is 0.5 x squared plus x plus 2. Okay. And this part we are saying sklearn, pre-processing polynomial features. So we are basically adding the polynomial features. This is polynomial features, and then we do the fit transform, which does the model, as in which does the which does the curve fitting and gives us the result. Okay, and x poly now contains the original features of x plus square of these features. Okay, let me go back here. So what we have done just now is we have added some more features. That's all. And it has added some more features. Then we are first of all trying to fit the linear regression. Okay. And then seeing the intercept and coefficient. All right. Okay, so all right, let me repeat the entire thing. So first of all, we created the line space for plotting. Then we have transformed these data points into this. Okay, we added the polynomial factors. Then we are predicting, and then we're plotting here. Okay. So let me go back where we were. All right. So what we are trying to do is, let me just talk about the same thing. So we can use a linear model to fit nonlinear data. We can add powers of each of the features as new features and train a linear model on the extended features. This is called polynomial regression. Okay. So first of all, we generated the data. This is the data that we generated. Okay. And then we use the polynomial feature class to transform the training data And what did we do the transformation? We added a square of each feature in the training set as the new features. Okay, so what we did was we generated these features with 2 degree, and then we did the translation. So afterwards, x0 was 0.75, while x underscore poly 0 contained one more variable. And this is nothing but square of this one. Okay, correct? So 0.75 square is how much? 0.75 into 0.75. So it's 5625, correct? It's 5625. So that way. Yes. So total number of features will become double. Okay. So if in general, what it does is it not only adds the square of a particular feature. If there are two features, x1 and x2, what it will do is it will, if let's say there were two features, x1 and x2, okay, and x2. So instead of only making it x1 plus x1 square, right? What it, okay, here there is some theta and so on. So what it does is it also adds things like x2 square plus x1 into x2. So this is the kind of, these are these are the things that it would add. Okay, so yeah, so x1 square, and this is better. This is the kind of extra features it has. So it would basically add, the total outcome will be these many features. So if there are d degree, if you have 2 degrees, then it will basically add uh, x1, x2, x1 square plus x2 square plus x1 into x2 and so on. In general, if there are d degree that you want to transform it to, these total features would be these many, meaning all permutations of x1 and x2 and the degrees. Okay, this is what it is. Yeah, in other words, you can say n plus d cn. Okay, n plus d cn. Total combinations, you can say, not permutations. That's right. The degree is the order of polynomial. Okay, so polynomial regression can help you find the relationship between features when plain regression is not, cannot do that. This is because polynomial features add all combinations of features up to the given degree. Okay, so for example, let's say there were two features A and B, and we are adding the polynomial features, or we are transforming it to polynomial features with a degree 3. It will add the following features. It will add a square, along with a, there will be a square, a cube, there will be b square and b cube, and of course it will add ab, a square b, and ab square. All right, now does it make sense to you? A question from Kamal is, but how do we know, looking at the data, that what should we choose as a degree of features? Okay, very good question. Very good question. That's what we are going to cover in details as we go ahead. Okay, is it clear? So polynomial features adds all combinations of the various features and their degrees. Okay. Yes, Noor. This is going to be both memory-wise and computationally intensive. All right. Now, here is an example. So now let's fit the linear regression model to this extended training set. Okay. So we essentially got 3 or 4 uh, parameters, and instead of only 2 features, there are now 4 features, and that's what it does. Here we are saying transform x new. Okay, so this was our actual data, and then we did this. Okay, here linear regression dot predict is what we have done. Okay, so this is the outcome. So this was our equation, and instead of the actual one, here it was 0.5, correct? It was 1 and it was 2. So this is the approximation our linear model has done. Okay, so instead of 0.5, it is 0.56. Instead of 1, it is 0.93. And instead of 2, it is 1.78. Is that right? Where is, yeah. So instead of 2, it is 2. Instead of 2, it is 1.78. This is how it looks like. So what we learned just now is that if in our data point, we add the features related to the quadratic or other degree values, then using the as in multivariable, multivariate linear regression can solve our problems. Okay. Okay. So as we have seen earlier, the high degree polynomial regression fits the training data much better than plain linear regression without extra terms. And take a look at the fitting of plain linear regression, then second degree polynomial regression, then 300 degree polynomial regression. And if you want to take a look at the code, take a look at the notebook. So the same data that we generated, if we try to fit different kind of polynomial regressions, this is the result we get. Okay, out of this, one is this, which is a straight line, which is definitely not fitting the data, right? This is our data, the blue one is our data. So this one is definitely not fitting it. Then second one, dashes, this is the one that's fitting our data closely, right? And with 300 polynomial degree, it's this. Okay, you can see that it has underfit it is underfitting. Okay, it is underfitting. All right. Is it clear to all of you what we're talking about? Pavan, Noor, Kamal, Vintao, Balaji. So as we can see that from previous diagram, 300-degree polynomial model wiggles around to get as close as possible. Okay, so it tries to fit this data, and so on. It basically, whatever random data we have generated, it tries to fit that. Okay, so you can see that high degree polynomial model is severely overfitting the training data. Okay, so high degree polynomial regression is severely overfitting the training data. Okay, basically it's trying to fit even the ones with Gaussian noise. Okay, while linear model is underfitting the training data. Okay, underfitting as in it's trying to draw the straight line through the data. Okay, now a question is how do we find which one is underfitting or overfitting? Anybody? How do we find if the model is underfitting or overfitting? Anybody? Pavan, Noor, Kamal, Bintao, Balaji. Correct, correct. So we use validation methods. We compare with test data. That's right. Okay. So we essentially use the cross validation, right? So if a model performs well on training data, like perfectly well, but it generalizes poorly on the cross validation, this then model is definitely overfitting. Overfitting means it is trying to memorize everything. It's trying to even consider the noise as the data. Okay, so the polynomial functions, the extra degree ones, overfit heavily. Okay, they're just taking the things too seriously. Okay, every so then the model is overfitting. In this case, the model is too complex. Okay, if a model performs poorly on both training data and cross validation, okay, then the model is underfitting, meaning it would require more degree, and definitely the the algorithm that we have used or the hyperparameters that we are using is not sufficient to represent our need. Okay, so so as a thumb rule, if the algorithm is doing well on training but doing very bad on the test, okay, on the cross validation, we realize that the algorithm is overfitting. Okay, if it performs badly on both cross validation as well as the actual data, then we realize that there is something seriously wrong, and hence it could be underfitting. This is a quick way of understanding it. The another approach could be to look at the learning curve. Okay, to look at the learning curve. Learning curve are the plots of the model's performance on training data and validation set as a function of training set size. Okay, so on one axis, what we do is the we put the training set size, and on other axis we have the performance with respect to the training and test. Okay, training and validation both. So there are essentially two graphs in two dimension. And so what we do is in these cases is for every kind of batch size, for the input data size, we break it down into batch sizes. For every kind of batch size, we generate the we generate the validation and testing results. Okay, so for we simply train the model several times on different sized subset of the training set. Okay, so we first train on 10 records, then 20 records, then 1,000 records, and 2,000 records, and 1,000,000 records, and so on. We keep on doing that and keep on plotting the graph. Okay, so let's plot the learning curves. We'll train the model on different subsets of the training set and plot the RMSE and training size. Okay, let's take a look. So here is the graph. This would help you immensely in identifying whether it's underfitting or overfitting. So on x-axis, we have training set size. On y-axis, we have root mean square error. Okay, so here what we are doing is that let's say we took say 5 records first. Okay, for 5 records we computed the RMSE on training set and on validation set. So here the error in case of validation is too high and this delta is too high. The difference between actual or validation versus the training is too high. And as the data grows, okay, so all right. So when there are just 1 or 2 instances in the training set, the model can fit them perfectly. This is why the curve starts at 0, right? So in other words, you can say that using 2 data points, we can always draw the straight line, and therefore there will be always the error will always be 0. Okay, so if we have very few instances in the dataset, our algorithm will memorize that, and basically this is how it will overfit. Okay, so you can see that there's a huge difference between training and validation, though the root mean square error is low at this point. But as the new instances are added to the training set, it becomes impossible for the model to fit the training data perfectly, both because the data is noisy and because it is not linear at all. Okay, so as we keep on adding more and more training set, okay, more and more data to the training set, and we keep on comparing the performances with validation and training, then what we realize is that it increases, and after a point of time it becomes a straight line. Okay, so since the data grows bigger, so model won't be able to fit it in or memorize it, and therefore we'll get better results. The error on the training data goes up until it reaches the plateau, as in it becomes kind of a straight line. Okay, at this point, adding new instances to the training set does not make the error much worse or better. Okay, so after a reasonable amount of data points, adding more data points to the training set does not help much. Okay, all right. So when the model is just trained on few data sets, what it will do is it will memorize those few data sets and will not really give good results in the validation. All right. So I hope this is clear to all. So since a straight line cannot do a good job of modeling data, so the error ends up at a plateau. Okay. And both are very close to the other curve. Okay. So these learning curves are examples of underfitting model. Why? Because both validation and training both are higher, meaning both have equal amount of error. That means it is underfitting. Okay, it is underfitting the model. Do it make sense to you? All right. So basically, both of them are learning here. Had the both lines been really low, or could have come down to a lower side, then the result could have been so that then it could have been it would not be underfitting them. Okay, let me repeat what I was saying. Now this is underfitting. Why? Because both after a point of time when we have sufficient data, both validation and training have decent amount of error. Have decent amount of error. Okay. So if the model is underfitting the training data, then adding more training data will not help. Okay, we'll need to use a more complex model or come up with better features. Okay, let's plot the learning curve or 10-degree polynomial. Okay, so here what is happening is that initially the error is 0, but on the training data set, while this is on the testing data set. So what are we trying to do? We are trying to plot the learning curve. What is a learning curve? In learning curve, what we do is for different data sizes or data batches, we observe the difference between the validation and training root mean square errors. Okay, so we compute the errors in both cases and then plot that on a chart. Okay, so what we have here is the training set size. If it was 10 records, the algorithm was able to memorize, but when it applied the knowledge on the validation, it gave us huge errors. This is the huge error. And then as it starts to learn better, it does more errors, as in the root mean square error is more. And after a point of time, it kind of subsidizes. It kind of becomes plateau, kind of becomes straight line. Okay, so you can see that what is your observation in this kind of plot? So here we have a 10-degree polynomial model. What do you see here? Correct. So okay, the error on the training data is much lower than the linear regression model. The error on the training data is much lower than the linear regression because in the lower ranges. So and there is a gap between the curve. That means the model performs significantly better on the training data than the validation one. Okay, so till the 10 records, till the 10 records, the model is memorized everything. You can see that, and is performing really great on only on training data. But on testing, it's completely wrong. On the validation, it is found that whatever we have learned here is rubbish. Okay, because on validation, there is a huge error in this. Okay, and as the data keeps on growing, the two curves keep on touching each other and going closer. So one way to improve an overfitting model is to feed it more training data. Okay, so if you have a model that's overfitting, then you keep on feeding more and more data so that it learns better. Okay, it's like saying that if you have you are from a small town and you have not seen much of the world, you should see more world in order to become more open-minded, instead of saying that all people who have these characteristics behave like this. Instead of that, one should see more data, learn from the bigger world, and then the overall training will be better. Okay, so all right, is this the one, Noor, you're looking for? So initially, if an algorithm has only seen a small world, then it kind of memorized it and thinks that this is correct. But at this point, when we validated its knowledge, it's not correct. It's only very limited. And as the data keeps on growing, the algorithm keeps on making more mistakes. It does more error, while the overall validation, the validation becomes more and more uh, closer to the to the same validation of the testing data. Is this the one? Okay, all right, great. So a question from Noor is, so when error is high, no matter how much data is there, it will keep on, it'll be underfitting. Yes. Okay. All right. So coming back to this slide. So if the model performs well on training data, but generalizes poorly, that means that the model is overfitting. Okay. In case you get into this kind of scenario here, remember in the first project, what when we run the random forest one, we got the zero error. It was this scenario. It was this scenario. Okay. And so, all right. So yes, let's talk about bias variance, bias versus variance trade-off, and we will talk in a little bit more details tomorrow. Then we'll continue to the regularization parameters, and then do the classification, and then we'll start the SVM. Okay. So yes, great, great. So far we have learned the most important part of the machine learning. One, what we've learned is we have learned the basics of end-to-end project. Second, we have learned the classification. Third, third most important part we have learned is the gradient descent. Gradient descent will be used in almost every circumstance as we go ahead. Okay, there will be more applications of the same. All right. So thank you, everyone. I look forward to see you tomorrow. Have a good day. Thank you, Abhinav. Thank you, Balaji. Thank you, Bintao. Thank you, Kamal. Thank you, Noor. Have a good day.